Okay, wonderful. We are delighted to have Bjoern Schenke back for the second of two seminars. Bjoern, thank you so much for coming. Brief recap of the bio. Bjoern is a scientist in the nuclear theory group at BNL, working on the theory of nuclear matter under extreme conditions of high temperature and density and nuclei at high energy. He received his PhD in physics in 2008 from Goethe University in Frankfurt, Germany, and after spending time as a Tomlinson Postdoctoral Fellow at McGill University in Canada, joined BNL in 2010. Bjoern received the DOE Early Career Award in 2014 and is a fellow of the American Physical Society, and in general is one of the absolute world experts in fluid dynamics of quark gluon plasma, and in particular looking at applying viscous relativistic hydrodynamics in small systems, which is, I think, what we're going to hear about today, and I'm very excited to hear about. So Bjoern, when you're ready, please take it away.
Okay, thank you so much. And so thanks again for the invitation and the introduction. So you see, this is a continuation of the last seminar, and I said latest applications, and I will focus on the applications, obviously, that I've been involved in. Not entirely, but mostly. So you've seen this in the last seminar, which is sort of the general structure of simulation frameworks that we're going to be using. And here I'm going to have two main examples that I would be talking about, which is simulations using the IP Glasma initial state. That's going to be 2+1D simulations with this initial state and then followed by hydrodynamics in 2+1D. And then we're going to use a 3D extension to the Monte Carlo Glauber model, which I will explain, which will then be fed into 3+1D hydro simulation. So this is something I summarize in this slide. With the first one, we're going to look at things like flow in proton-lead collisions, nucleon substructure, and what we can learn about that in PA, but also in heavy ion collisions. And in the second part, I will talk about this 3+1D simulation and focus on the RIC small system scan. So that's something that the Phoenix collaboration led, and with the goal of seeing whether really in small systems we have strong final state effects, or if this what one has observed are effects that come from other sources. And I will also, if I have time, address ultraperipheral collisions. And that really means we have a photon colliding with a nucleus, and see if we can have flow and strong final state effects in such a system. I will address the applicability of fluid dynamics and basically try to address the question why fluid dynamics seems to work so well, even though the system is very small and produces only on the order of 20 particles or so. And then I'll just briefly mention some other recent results from the 3+1D simulations, but probably just in one or two slides. Okay, so let's get started. Flow in small systems. So we've seen last time already that over a wide range of multiplicities, in fact, several orders of magnitude, fluid dynamics does a pretty decent job in describing these flow coefficients that I introduced last time. So this is the V2 measured with two particle correlations in lead-lead, xenon-xenon, and proton-lead collisions. And you see, particularly for the high multiplicities, this works pretty well. Here's some discrepancies, but these are details which you could probably improve by fine-tuning the parameters, by doing, for example, a Bayesian analysis or so. This has not been done here. In fact, the parameters of this calculation were all fixed at RIC, and this is all LHC data. So this is actually an extrapolation, and still it works very well and describes, for example, the difference between the different systems very well. In proton-lead, first of all, we didn't have enough statistics to go to the highest multiplicity because that's in the tail of the distribution, and be a little bit low. But again, you're very close, right? Even though this is a very small system, and you're only looking at within a range of a rapidity of size 1.6. So that's the longitudinal momentum measure. You have what? You have only like 40, 50 particles, right? And still hydrodynamics works well. So the question will be why, and also what we can learn from this. So once again, now specifically to this IP Glasma plus music framework, I have this chart. So we start with IP Glasma, which I will explain in the next few slides. very briefly though. At a time of 0.4 Fermi, we switch to fluid dynamics, and that's done by matching the entire energy momentum tensor. Remember, that's sort of our initial condition. And then hydrodynamics just deals with the conservation of energy momentum, as I introduced last time. And then at a temperature of roughly 145 MeV, I say roughly because we actually fixed the energy density surface, we switch to a microscopic transport code. So we sample the particles from the surface, which I explained last time, and feed them into this URQMD code. And then the equation of state comes from lattice QCD, also addressed this last time, that's fed into the hydrodynamics. Everything is described in detail in this paper. We called it running the gamut because we tried to describe all the available systems over all the different energy scales within this one framework. And so let me just start by explaining this initial state. I won't go into too much detail because it could take an entire hour to go through all that, but just roughly to explain what goes into it. So this IP plasma is essentially based on the effective theory of QCD called the Quark Gluon, called the color glass condensate. And this color glass condensate is sort of the state that my incoming nuclei are in at high energy, right? So QCD basically tells us through this effective theory that what is colliding are mostly gluons if I'm colliding at small x. So this is sort of the x range, and you can think of x as essentially the transverse momentum scale divided by the energy, and it is in a certain frame the longitudinal momentum fraction of my parton inside the proton or the nucleus. So this will always be sort of around 10 to the minus 3 or below, at least at mid rapidity. And you see you have mostly gluons. These are factors of 0.05, right? So relative to the valence quarks, the gluons are tremendously enhanced. You see actually the C quarks are not too far below, but we're going to ignore them for the sake of simplicity. So then below a certain transverse momentum scale that we call saturation scale, QS, these gluons are saturated. And this is just a consequence essentially of unitarity that this growth cannot really go on forever. Eventually it has to be dampened. And it's dampened by the fact that gluons cannot just split, but they can merge. And once the probability for merging becomes comparable to the probability for splitting, we get into this nonlinear regime and we have gluon saturation. So in this regime, and so this happens once the occupation number of gluons are on the order of 1 over alpha s, the strong coupling constant. And so these are large occupation numbers. And whenever you have a lot of stuff, right, you can start to ignore quantum effects. So we can have an effective classical description. And that's described by the Yang-Mills equations. So the whole system is described by that. And you could also include leading quantum corrections. So the leading logarithmic corrections are included with the Jim-Walk equations, or the large NC version is the Balitsky-Kovtchekov equations. But in this talk, I won't do it. But we actually are also working on that for the initial set of heavy ion collisions to include these effects. Now, as I said, the particle production is governed by Yang-Mills equations. So this plot just actually shows the color charge density distributions. From these density distributions, you would sample. So first of all, you get these by sampling a Wood-Saxon distribution like I described last time. This gives you the nucleon positions. Then you have some parameterization that for each nucleon, you have some Gaussian shaped transverse distribution of color charges. Then you sample color charges, basically like in a McLaren-Van Paalen model, where you say they are just Gaussian correlated. So it's just a white noise distribution of color charges, but following this spatially dependent distribution. And then the sizes of these blobs, we constrained them from EP scattering data from Hera. So as I mentioned, I think in the discussion last time, and I will come to this in more detail, there's certain observables at Hera that are sensitive to the size of the proton, and we used this information on the size of the proton here to constrain the nucleon size inside the nucleus, assuming that inside a nucleus, this is not too much modified. So once we have these color charges, they form essentially the color currents of the Yang-Mills equation, which I drew here. So this J nu is constructed from these color charges moving at the speed of light. So each of these nuclei gives me a contribution to this J nu. And then I solve this d mu, f mu. F mu is the field strength tensor, which has the gluon fields in it. And this is the covariant derivative. And I can solve that. I get the fields of the gluons that are produced from these color charges, right? So the dynamic gluon fields in these incoming nuclei are A and AB. And then I can solve for the gluon fields after the collision, which is this AI and A eta, and these are just combinations of these. In practice, we do this on a lattice, so we actually have to do this in terms of Wilson lines. I won't go into the details of that, but there's a lattice formulation of this, which has to be done for consistency. And so then we can solve for the gluon fields in the forward light cone. And then the gluon fields and forward light cone, they are stuck in this field strength tensor here, and we express it here now as these components of F, but also sort of color electric field components. But these are all coming from the gluon fields A that we solved. And this time evolution is illustrated here. I'm plotting the energy density. Actually, I'm just plotting the tau component of the energy momentum tensor as a function of time. You see it here evolving. And what I'm also plotting is these 4 different colored components, which are the longitudinal magnetic part, the longitudinal electric field part, and then the contributions from the transverse magnetic and transverse electric field. And you see, initially, we only have longitudinal electromagnetic fields. This is sort of these color flux tubes you can think of, but the transverse components quickly rise, and then eventually we have sort of this equipartition of the energy density. And on the left-hand side, you see how, well, we have this 1/tau drop-off, right? But then also you see the smoothing of the distribution, which we briefly addressed last time as well. So this is what this T mu nu looks like, or at least the T tau tau component looks like. And so this is what we're going to plug into the hydrodynamics, right? So this distribution here, including all the other components, Tij and so on, which have some viscous corrections in them. So this is what we feed into hydrodynamics. I want to say a few more words on what I started addressing, which is the size of these blobs and also the substructure of these blobs for each nucleon, right? So how do we get these color charge distributions? So as I said, for a nucleus, we sample the nucleons, and then for each nucleon, we consider some substructure, and both the size and the substructure of this nucleon is constrained by Hera data. And this is the Hera data I'm talking about. So this is a diffractive J-side production. So I have an electron colliding with a proton. I have an exclusive process where the only thing I'm producing is a vector meson, in this case, a J-psi, so a CC bar bound state. And I'm looking at the case where the proton does not break up, that's the coherent, and the data is these solid points. And then the other case is where the proton does break up. That's the incoherent case, and that's these open circles. So you see at low transverse momentum transfer, or a Mandelstam T here, essentially that's the transverse momentum of the J side that's measured, squared. At low T, the coherent dominates. And the coherent, in fact, is sensitive to the size of the target. So via Fourier transform, right, this slope here essentially is the inverse of the target size. So if this was steeper, it means my proton was larger. If it was flatter, my proton would be smaller. So from this, in the model, I have a parameter that describes the size of the proton. I can constrain that. Okay, so by fitting this data here. And then I have 2 sets of curves, right? I have the dashed and I have the solid. The solid curves are the ones where I include substructure fluctuations. So the proton will have some hot spots that fluctuate around. And the dashed ones are where I don't have that. So for the overall size, obviously, it doesn't matter much whether I have substructure or not. So I can kind of describe this data in both cases fairly well. There's some differences, but I think actually tune this such that both would work better. But the point is that in the incoherent case, I'm actually sensitive to fluctuations of the scattering amplitude, and that includes fluctuations of the geometry. And obviously, if I have substructure, the geometry will fluctuate a lot more. So without substructure fluctuations, I have this dashed line, essentially an order of magnitude or so or more below the data. But once I include substructure fluctuations, I can describe the data. And this is described well because I have some parameters to tune, which are the size of these hotspots and the number of hotspots and so on. So to give you an idea, in the round proton case, I get a typical configuration of a proton that looks like this. So this is, I think, just sort of a trace of Wilson lines, just to give you an idea of how the gluons are distributed. That's not perfectly round because I have these color charge fluctuations that I have on top of the smooth average shape. But on average, typical events will look like this, so pretty round. But if I have substructure, I have, in this case, 3 hotspots. So one example configuration would look like this, right? So the hotspots are arranged like this. And then if you think of, how else they could be arranged, you have a lot more fluctuations than just this round thing, which has tiny fluctuations just from the color charge fluctuations. So my typical proton actually doesn't look like this, but looks more like this. And in fact, that's something that's in this model, at least in this framework, needed also to better describe the proton lead data. So here now I show you again 2 different curves, one solid, one dashed, and I'm comparing to V2 and V3 measured in proton lead collisions. So now a completely different system than what we discussed at Hera. And I'm plugging in now my initial distribution for the proton and also for the nucleons and the lead, either to be something like this or something like that down here. And you see that if I don't have these additional fluctuations, I underestimate the data significantly. If I include them, I can do better, much better, in fact. I'm still below the data here for V3, but there has no fine-tuning been done here in terms of trying to fit, all the p-lead data. But
quick question.
Yeah.
Does this have this direction in which this is going? Does this have something to do that your objects with substructures appear to be smaller initially, but there's more to push this thing away in terms of gradients?
It's I think a small part of it. So I think the mean PT will be also a little bit larger, but I think the main effect here is actually the eccentricities being different. So because this is almost round on average, and I show actually in the next slide that you basically the fluctuations inside the lead don't matter too much. The lead kind of acts as a canvas to image the shape of the proton, right? In the projection of the shape of the proton. So if the proton looks like this, you have very small eccentricities. It's almost round up to some small small differences. But if you have something like this, you can have a large epsilon2 and a large epsilon3, so large eccentricity and triangularity, bringing these up. So that's, I think, the main effect. And yeah, here's what I was just talking about. So this is just to show you that what I said is valid. So what I'm showing is 2 different plots on top of each other. One is the color map here, which is the energy density distribution. After I do this whole calculation that I said, right? So this is essentially taking the energy density that's inside my T mu that will be fed into the hydro. And the contour lines are the shape of the projectile, quantified again with just a trace of a Wilson line inside of the proton. So this is just to show that really I'm kind of imaging the shape of the proton here in this energy density distribution. There is additional fluctuations coming from the fact that the lead is not perfectly smooth, right? It also has fluctuations inside. But to first approximation, right, I'm looking at what does the proton look like as I take this snapshot when I do the collision. So about this nucleon substructure, so is this really true? You may ask, oh, there have been Monte Carlo Glauber-like or Monte Carlo Glauber models before, and they didn't have substructure. And actually, they did a good job in describing p-LED data, for example. So this is two examples. So there's some older calculation from Božic and others compared to Atlas data. What's shown here is V2, so two-particle correlation V2, and then also V2,4. And this is a calculation with a Glauber model, which does not include subnucleon structure. And they describe the data, reasonably well. And even better in this calculation, which is, I think, by Chun Chen and others. And again, you describe this data very well, and you don't have substructure. So what's the right answer then? Do I need this or do I not, right? So it depends on the model. So first of all, how do these models differ? So in the Monte Carlo Glauber model, what can be used and what is often used is just sort of the sum of thickness functions, for example. Not necessarily for all of them, but this is just an example how different this would look to the IP plasma. So I'm plotting here one set of configuration of nucleons. So you see when you compare these little open circles here, if you can see them, they are identical between the two pictures. So the nucleon positions are identical. And now I just take a different model to determine what is my initial energy density distribution. And then the Monte Carlo Glauber model, where I just take TA plus TB, so that's the thickness function from the proton and from the nucleus. So I take the wounded nucleons, so the ones I determined have collided in the Glauber model, and put some energy density for them. I get this distribution. So it looks very choppy and has some eccentricities to it. Whereas in the IP plasma, you can think of it more as coming from the product of thickness function. At least that's true in the dilute limit. And then you just get basically, as I said before, the shape of the proton out, right? So the TA, let's say if that's the proton, that dominates. So they look very different. And you can see that even without substructure, you will have a lot of fluctuations. You get large eccentricities. You can get large V2 and V3, right? Now the question is, what is correct, right? What should be correct? So there is some arguments that tell you should not use the sum of thickness functions, but you should have something like the product. And that's coming from several pieces of evidence, I would say. So, so what is preferred, according to, for example, Bayesian analyses that have been done, many different Bayesian analyses, is that the energy or entropy deposition should go like TA times TB to some power Q. That's been done, for example, with this Trento model that I briefly mentioned last time. So that's just a parameterization of how this energy deposition should go. So essentially, it's something like TA times TB to power Q or so. It's a little bit more complicated. So it can go from TA plus TB to square root of TA times TB and everything in between. And what all these analyses find is that the square root TA TB is preferred. And that also prefers a nucleon substructure, because otherwise it will look more like this, right? As soon as you take a product or the product to some power, you will follow the proton shape. And if the proton is round, your eccentricities will be too small in this case. Also, different sort of more fundamental calculations give you dependencies that look sort of like a product to some power. So ADS-CFT-based calculations have shown this. The IP plasma results, at least in the dilute limit, also go like TA times TB, as I said. And there's another paper that showed that TA plus TB is disfavored by the centrality dependence of E2 in AA collisions. So there's several hints that it should not go like TA plus TB, but like a product to some power. And if that's the case, we do need subnucleon fluctuations to describe the data in the small systems. So this is an argument for that there is some substructure, and actually we find more or less consistency between HERA data, which needs the substructure, and the p-LED data that I showed that also needs the substructure in the same framework. Now, another question you could ask is, do we actually agree on the nucleon size, right? So first of all, this nucleon size that we extract from the HERA data is not the charge radius, right, of the proton in the HERA data case. It's really more of a gluon distribution that we're sensitive to because we're probing a relatively small x. So it's more related to this sort of mass radius that's also been determined through threshold JSI production at JLab, for example. And that's always a little bit smaller, so that's about 0.5 Fermi or so, which is also what we find to be consistent with the heavy ion data. So that's about the RMS radius or so of our nucleons. And then we have these hotspots of the substructure. Okay, these are 0.1 Fermi. But let's focus on this nucleon size first of all. So as I said before, we use a Gaussian, right? This is 2Ds, it's projection, right? TA is already integrated over the longitudinal direction. And similar values have been used in the past, but some newer Bayesian analyses from like 2019 to 2021 found values that were much larger, actually larger even than the charge radius. So the question is, which one is correct, right? So actually, I wanted to show you that makes a big difference in what these energy density distributions look like. So Giuliano, Giacalone kind of compiled these. So these are different Trento models and Bayesian analyses. This is an older one, I believe. And then the newer one actually found a much smoother. So that's the one with like 1 Fermi size nucleons. Then there's another one, which again has a smaller one. Then the IP plasma, you see, I think that's maybe what you referred to last time. There's some holes in it, so there's very small hotspots. Possible that's because of the substructure also. But this is at very early time, 0.1. Once you evolve to 0.4, these are already smeared out a little bit more. And then there's a Jetscape one, which is also very smooth, and then one in between again. So anyway, so we don't agree on the nucleon size, and these look quite different depending on what we use. And what the fits do in the Bayesian analysis, for example, is to really trade larger W for smaller viscosity. So if you make W larger, right, you'll have less of a outward push, right? And you have less eccentricity as well. And then you have to compensate that with medium properties, right? So the question is, can we actually leverage some observables that can distinguish these two cases, or can pin down this nucleon size independently from the medium properties, right? So we need an observable that's sensitive to only one of them, right? And maybe we're missing information. So there's been a paper by Govert Nice and Wilke van der Skee, and they have looked at what happens if you actually include information on what the nucleus cross-section should be. So that's very fundamental observable that's usually not included as information in these Bayesian analyses. So the nucleus cross-section has been measured, and actually I didn't put the reference here. I think it's Alice that measured it. Yeah, I hope that's correct. I should have put the data reference, but you can find it in this paper. And then, that value has been measured, and then they kind of computed what this quantity is in their model as a function of the size of the nucleon that they put in. And you see in their calculation that actually constrains the nucleon size to be, close to 0.5 or so Fermi, instead of the close to 1 that they had previously. So then they would overestimate this nucleus cross-section. And moreover, there's another observable that can distinguish between these, which is the correlation of the mean PT with the V2. So essentially, you're looking at fluctuations of mean PT and V2, and you can define this covariance measure rho that kind of measures the deviations of V2 squared and mean PT from its average in some centrality bin, right? And then normalizes this by these individual delta V and delta PT squareds. The hat means I kind of remove variations of this observable Vn or PT by removing the multiplicity fluctuations. You can also achieve this by taking very small centrality bins of like 1%, which is what the experiments are doing. So this is what has been suggested by Božič quite a while ago as an additional observable that might carry interesting information. And indeed, it seems to be quite a powerful observable. For example, and this is a messy plot, so I walk you through it. But for example, it can distinguish, or it has some sensitivity to the nucleon size, while not being too sensitive to the medium properties. So all these different curves, first of all, there's data from ALICE and ATLAS. Let's focus on the ALICE data because that has the same PT range actually as these other colorful lines. The blue line is our standard calculation in the IP plasma plus music, where we have the substructure. So that's using the W of 0.4 Fermi and substructure of 0.1. And then you see the blue one, okay, it's a little bit above for V2, and it's basically on the data for V3 PT correlations. And then what happens here is I increase the nucleon size, right? So I go from green to magenta to gray, and I increase more and more. And eventually you see even the sign doesn't work out anymore, right? The difference becomes larger and larger to the data, especially if you look at V3 PT correlations. The gray and the magenta really don't work at all, whereas the green and the blue are okay, right? So these are the ones that prefer the small, or that use the small nucleon size. To see that it's not too sensitive to viscosities, we actually changed the viscosity. I don't remember by how much, but at least a factor 2 or so in the yellow curve. And so there you see the gray curve here and the yellow one are very much on top of each other. And also here on the left plot, they are very similar. So you see there's not too much sensitivity to the medium properties, but you are very sensitive to the nucleon size. And then there's a curve from Jetscape, which uses a large nucleon size. And you see that's also consistent with the large nucleon ones that we used. And you see in this other paper where they included this nucleus-nucleus cross-section, and there's also a clear, where they preferred this small nucleon size with this constraint. In that case, also they described the data much better for this row correlator. So this is the same thing that I showed you in the previous slide. These plots are a little bit cleaner because they don't have so many curves. But this is the row 2, the row 3, and even the row 4. And what they call weighted and sigma AA, and sigma AA means they include this constraint for the nucleus-nucleus cross-section. And the red one is where they don't include it. Don't worry about the weighted, unweighted. That's really sort of how much they weigh different observables in their Bayesian analysis, depending on how large the errors are. But you see that in particular for row 3 here, the data is much better described. Data is just these solid blobs by this blue band, which includes this constraint and uses a smaller nucleon size than by the red one. So again, this is a consistent picture that says we need a sort of nucleon size of like 0.5 Fermi or smaller, and not 1 Fermi.
Another one on this, if you play with the substructure, does that affect these plots?
It does, but not too much. So this is essentially the difference between the blue and the green curve here.
Okay.
So the green doesn't include such substructure, and the blue one does.
Okay,
and you see they're identical at more central collisions, but then there's some difference as you go more peripheral here. For the row 3 correlator, there's not much difference within the statistics that we have. Yeah. Okay, so that's actually some nice things we could learn already. But I want to first come to a different topic, or a slightly different topic, which is going to be using the 3+1D collisions simulations, and focus on the small system scan at RIG. So I talked about that hydrodynamics works pretty well in describing proton-led collisions, and we're sensitive to the proton shape and geometry. And but this whole these all observations about whether hydrodynamics works or that hydrodynamics seems to work in small systems triggered this project by Phoenix, who wanted to see whether really if I modify my initial geometry, right, does that modify my observables, right? If it doesn't, it could mean that it's actually not the geometry that drives these observables, And that could mean that that there's no strong final state effects, right, that are important in a small system. It could be an initial state effect where, you know, these anisotropies are born out of the initial state already by, say, the color gas condensate features or so. So they suggested to look at proton gold, deuteron gold, and helium-3 gold collisions. And in a simple model, which doesn't include substructure actually, you have very clear expectations that the epsilon2, that's the eccentricity, so the eccentricity of your initial shape, or ellipticity, I should say, is very different in deuteron gold, because in deuteron gold you would have two blobs, right? So it's much more elliptical overall than in a proton, which is just one round blob. And then in helium-3, where you have three blobs, you know, it's still very similar to deuteron gold. And the triangularity is expected to be much larger in helium-3 gold because you have three blobs, right? And then there's a good chance that they are arranged in like a triangle shape, which you cannot do with just two blobs, right? So this is what you expect as the sort of difference. And then they did the measurements, and what they found is essentially exactly what they expected. The red one here is proton gold. It's smaller in V2 than deuteron gold and helium-3 gold. And for V3, you see the deuteron gold and proton gold are similar, just like the expectation, and the helium-3 gold is larger, right? So that's what they found, and then their conclusion was, yeah, this is driven by geometry, right? It followed exactly the expectation. So what's happening is you have these initial states. Sometimes they look triangular, not always, right? This is a very specific example that they chose where it actually looks triangular. What's really important is the average eccentricity here. But anyways, then they see this evolves, and then you get some triangular shape momentum distribution in this case, for example. Much more so in helium-3 gold than in the other two. Now, we wanted to simulate this, and we wanted to do this in 3 dimensions, because actually, in the end, it turned out that that is very important, and you will see. So we're using 3+1 dihydro, obviously, and then we have to have a model that gives us a 3-dimensional initial state. The IP plasma is in the high energy limit where everything is boost invariant. So while we have started going towards 3D IP plasma, which involves gym walk evolution and things like that, which gives us some longitudinal structure, that's not at the point where we can really do these full simulations. And also it doesn't have things like, you know, a net baryon distribution and so on, which we also included here. So we came up with a more phenomenological model, which is based on the Monte Carlo Glauber model. So the transfer structure is determined the same way as in the Monte Carlo Glauber model. And then for each wounded nucleon or valence quark inside that, we basically think of attaching a string between the two colliding ones, and then the string is decelerated, so these guys lose energy by their interaction as the collision happens. And then the energy and momentum that is lost is sourced into the hydrodynamics as a source term, right? So we feed in the energy lost by the individual valence quarks here in the collision. And that provides a fluctuating energy density distribution in the transverse as well as in the longitudinal direction. So this is sort of an example of a deuteron gold collision at 200 GeV as a function of space-time rapidity and transverse space where these strings are, right? So you see this is a very choppy distribution, both in this direction as well as in the rapidity direction. You see, of course, there's overlap, but you see also there's many more strings here. That's the gold going direction. And then over here, so you have a strong dependence on rapidity. And we'll look at this in plots that are better to understand in the next few slides. So to walk through just briefly through this model, so collision geometry, as I said, is determined by the MC Glauber model. That's the geometry in the transverse plane. Then I sample 3 valence quarks from a PDF and make sure that the sum of the X values is less than 1. And that the average PDF is still reproduced. So you have to sample in a smart way. And then we randomly pick one of them to lose energy in a nucleon-nucleon collision. And that's done by essentially putting the string in between and slowing them down. And then this energy that they lose is distributed along the string. So that's essentially a distribution like that. So that's assumed to be flat and then drop off, like I think with 2½ Gaussians or so for each nucleon-nucleon collision, right? So if you have many of them, essentially for each line in this plot here. And then the remaining energies are deposited at the string ends. So whatever they haven't lost, right? They still have. Same with the momentum. And the baryon density is either deposited at the string ends as well, or we also actually, and that's not so important for the next topics, but for maybe one of the last slide I will show, that we also have the option to have these baryon densities fluctuate toward the center of the string, and that's motivated by these baryon junctions, a model where instead of the quarks carrying a fractional baryon number, the baryon number is carried by a small x object, which is the so-called baryon junction. That's from an old paper by Kazeev, and so we're also testing whether we can see that in these models. Anyway, so we imposed in this complete conservation of energy, momentum, and net baryon density. And we constrained parameters by looking at proton-proton collisions. So for example, how much energy is lost in this deceleration, right, depends on, essentially what we put in. So we have a phenomenological curve or function of how much rapidity is lost given the initial rapidity of these guys. And then that is constrained by looking at proton-proton data. And for example, the multiplicity distribution, right, depends strongly on how much this fluctuates. So this band, in fact, is the 1 sigma band of the fluctuation of this quantity. So when we sample how much energy is lost, we sample it from this curve with this, with this width. And then we constrain the parameters of this by fitting, for example, this multiplicity distribution in PP. And this is the rapidity distribution in PP. It works fairly well. We kind of overestimate the data at mid-rapidity in proton-proton collisions. But, the shape otherwise is fairly well described. Equation of state, now we need one that has the ability to describe a system with finite mu b, mu s, and mu b at least. In this case, we actually choose that the total strangeness is 0, so we don't consider strangeness fluctuation. And we fix the charge NQ to be 0.5 times the baryon density, which is good for gold-gold collisions because of the ratio of protons to neutrons. And just to test whether the chemical pieces of this are correctly described, we looked at particle ratios, so kaons over pions, for example, and then also p bar over p, and so on. And you see, as a function of collision energy, this is fairly well describing the data. I just wanted to mention that for a more general equation of state that doesn't have these two constraints, but really is 4-dimensional in temperature and these 3 densities, we have a new paper on that as well. But for here, we kind of fixed these. Now, one more thing is the centrality definition. So Phoenix measured now, these quantities in these flow observables in certain centrality bins. And one thing that's important, and why this 3D description is important, is that actually the rapidity distributions depend on how you define the centrality. So on the left-hand side, these plots use a centrality definition based on the multiplicity in a detector that's close to mid-rapidity, whereas on the right-hand side is the V0 trigger, which used some forward measurement of multiplicity, right? So you see the rapidity pseudo-rapidity ranges here, and you see the shape of the rapidity distributions is different, and also the averages here are somewhat different depending on where you define your centrality. So with these 3D models, we are able to actually define the centrality in the same way that the experiments do. If your calculations is always flat in rapidity, right, you don't get these effects. And so let's look at more closely these rapidity distributions. So when we do this and we tuned all the parameters of the rapidity laws, etc., then we get multiplicity distributions, the function of rapidity in the 3 different systems. So the 3 plots are proton gold, deuteron gold, helium-3 gold, and then we look at different centralities. And this is the result on the right-hand side for helium-3 gold. So it's actually pretty well described. Deuteron gold as well, and proton gold. We underestimate maybe a little bit in this in the forward rapidities and the positive rapidities, but overall I think it's a good agreement compared to what a boost invariant model would get, which is a straight flat line. Right? Net baryon distributions also, again, not too important for us because we're not worrying so much about identified particles and what we're going to look at, but we also described the net baryon distributions fairly well. Of course, most data is only at mid rapidity, so we don't have the full distribution measured, but it's doing an okay job. So now let's look at the anisotropic flow. So first of all, flow as a function of rapidity is shown here. And compared to data from Phoenix, it's reasonably well described. These are in the most central bins, 0 to 5%, in helium-3 gold and deuteron gold. As you go to proton gold, you're not doing so great anymore. So in particular, in the proton going direction, you're underestimating this much. But the reason could be that this is from 2 particle correlations in principle. Well, it's event play method, they say. So, okay, same idea. So if it's event play method, they determine the event plane. So that's sort of the direction of with the angle of with respect to which I measure the V2. That's determined around -3 to -4 in rapidity. So if now my particles that I correlate with this event plane are also close to that rapidity, right, I will have a lot of non-flow effects. So effects from, resonance decays and other jetty things. I will correlate a particle that came from the same resonance, say, with another one that came from that resonance, and then I will have contributions to V2 from that. So there's probably non-flow in these small systems as as this gap in rapidity is removed. This effect we don't have in the calculations. We don't have individual resonance correlations. We already averaged over those. So this could explain this discrepancy down here in particular. So one important thing now is when you have this 3D structure, you have decorrelation of the flow vector. So flow vector just means it's the amplitude of the V2, say, but also the direction. So it's a complex number in principle that describes the direction and the magnitude of your flow. So this is for Q2, that's this vector, and Q3. And again, the reference is determined here between -3 and -4 or so. And so that means my Q2 as a function of eta is perfectly correlated with that, right? So we're close to 1. But as I go away in rapidity from my reference bin, this correlation decreases because the geometry changes, right? Because I have a structure in the longitudinal direction, this decreases. And the important point here is that for proton gold, this decorrelation is much faster than for the other 2 systems. And for Q3, for the third harmonic, there's actually a larger difference between helium-3 and the other 2. So you can see now that this hierarchy between the different Vn in our model is actually driven more by the decorrelation, or a lot by the decorrelation, and not so much by differences in eccentricities, which was sort of the motivation that Phoenix had. If we look at our eccentricities, they're actually fairly similar because we have this substructure. When you look at eccentricity, I don't have a plot here, but if you look at the eccentricity differences between the systems in a model that has substructures, they're much more similar than what the idealized Phoenix estimate shows, where they don't have substructure that are shown in the very beginning. But the decorrelations are much different because the systems are, if it's much smaller, it's easier to decorrelate them. Fewer strings in P gold. And so this decorrelation happens much more quickly. And so this actually also explains, at least in part, the difference between 2 different measurements. So I told you about the Phoenix measurement, which are the red points in this plot. But there's also been a later measurement by Starr. And if you look at the V3, they actually disagree largely in proton gold and deuteron gold. And one reason for that could be that they're measuring these things with different rapidity ranges. So I told you Phoenix measures essentially what is like two particle correlations, but they call it event plane, but they determine one particle comes from this negative rapidity bin and the other one comes from close to mid rapidity, right? So they have a large rapidity gap between here and here. Starr, however, measures everything in the central TPC. They enforce a rapidity gap of larger than 1, and they have another way to remove additional non-flow by some template fit. But they do see some difference, right? Large difference between the V3s, where the V2s are more similar. Now, in our calculation, we can now use the same rapidity ranges as the experiments do. And we see that we actually do see some difference between the different measurements, even though it's the same observable, but it's measured quite differently in different rapidity bins. And for the V3 in particular, it goes in the same way that we actually describe the Phoenix data very well everywhere. But for Starr, we still underestimate, but our calculation is significantly different also from our Phoenix calculation. And that's coming from this difference in rapidity bins. There may be additional differences that Starr might have still more non-flow, right? Because they don't have this huge rapidity gap like Phoenix has. You also see in proton gold, we actually, this goes even the wrong way. So there could still be even more issues with non-flow, or maybe hydro just not working, etc. So this is quite interesting, right? So this tells you have to do these simulations in 3D to get all these effects right. If you don't, right, what does it mean? So there was this old calculation, like one fluid to rule them all, etc., right? That compared to the Phoenix data. This is sonic and supersonic. Sorry, this is sonic and IEB Vishnu, both 2 + 1D simulations, right? So how do they get this decorrelation? Well, they don't, right? So we saw between this -3, where the reference frame is, and all the other, and mid rapidity, right? There's actually a factor of, I don't know what, 90% reduction, right? In P gold, whereas these models would just give 1 everywhere, right? So what does this mean if I compare this to the data? I don't know, right? The same issue is with IP plasma, right? Whatever boost invariance model you use, you're missing entirely this effect of decorrelation. And then, right, you have to compensate for it with, I don't know, different viscosities, etc. But you should run into trouble at some point when you want to describe large systems and small systems at the same time, etc., if you don't have the 3D calculations. I will skip over this in the interest of time and just go to questions about applicability of hydrodynamics, right? So there's been lots of work done, mostly by other people in the field, that were worried about, what happens in systems that are essentially 50 times smaller in volume than my central lead-lead collisions, right? I might have locally large Knudsen numbers, which is a number that reflects the macroscopic scale over a microscopic scale. Actually, the opposite, right? So your mean free path would be large compared to the system size. And also inverse Reynolds numbers, right? Which is the ratio of viscous forces to inertial forces. So if your viscous effects are too large, right, you shouldn't also trust this anymore. So this could lead to inaccuracies in your result, and also causality could be violated. And I'll come to that a little bit more. So there's now some new developments of alternatives to Israel Stewart-like theories, like, for example, BD and K, according to these author names, that can be shown to be always causal. So in our simulations, we use typically DNMR, like Denico, Niemi, Molnar, Rischke, which is a version of Israel Stewart with like a more sophisticated expansion in Knudsen and inverse Reynolds numbers. And then you can look at different causality constraints that these guys derived here. And indeed, there is situations where, one or the other constraint numbered here by N1 through N6 is violated, right? If they have negative values, then you have causality violation. This is in a proton-gold collision, the ones that we essentially just looked at. So there might be issues with that if that happens in the code. But the question is, why does it seem to still work so well? And one explanation might be that I reach so-called hydrodynamic attractors after a reasonable time of the order of 1 Fermi. And there's been calculations in like kinetic theories where people have looked at different microscopic theories, for example, just Young-Mills kinetics, Boltzmann with relaxation time approximation, some QCD kinetics or so, and you look at some quantities like energy densities or also pressures. They've looked at longitudinal transverse pressures and so on, and you plot this as a function of scaled time. And you find that while at early times you have some differences, but again, there might be close to free streaming actually. At late times, they all kind of converge to what viscous hydro would give you. And late times, I mean, okay, this is this quantity of order 1, which for reasonable values corresponds to the order of a Fermi or so. And so the validity of hydrodynamics may not really require thermalization or even isotopization, but merely what people have dubbed hydrodynamization. And that's achieved when the hydrodynamic modes dominate, right? So you have hydro modes and you have modes in your system that are, different, but typically these exponentially decay. And once all the modes that are non-hydro modes have decayed, right, it's reasonable to think that your system is well described by viscous hydrodynamics. And that's actually shown here, that's in fact happening in these different systems. In practice, right, if you're worried about what happens before 1 Fermi, because typically we start at 0.4 Fermi or 0.2 Fermi or so, then you could connect your initial state description more smoothly, right, with your hydrodynamic description by having some kinetic theory or effective kinetic theory model bridge this gap. And there's also core corona models where people use sort of the core of a system, that's the dense and high temperature part, and describe that by hydro. But the dilute edges, for example, are described from the beginning in a more like a particle cascade model, for example. So a combination of kinetic theory and hydrodynamics to be able to describe the dilute system better. Now, I mentioned this causality issues, and there's been some recent work that I just want to briefly mention. So people have derived these necessary and sufficient conditions for the system to be causal. And there's, for example, they made this plot of whether the system is causal or not as a function of 2 parameters. That's the bulk relaxation time and the shear relaxation time prefactors. And then they also plotted some values of previous Bayesian analyses where they lie. Many of them lie in the causal region, but there's actually, when you sample from a posterior in one of those fits, you find a lot of points that are actually in the acausal region. So now what happens if you do a Bayesian analysis, but enforce your system to be in the causal region? Then you get some modification. They claim you get some significant modification of what you extract for the bulk and shear viscosity. I don't see that there's a significant difference given these bands. These bands are sort of 60% confidence level bands in the Bayesian analysis. So your eta over S, changes mildly. The bigger change you can see in the bulk viscosity. However, these are still quite overlapping. But yeah, you see an overall, if you want, you see overall reduction of the bulk viscosity once you enforce these conditions. So this could affect somewhat, right? Where what you learn when you extract properties of the Quark Gluon plasma, whether your hydro, is allowed to violate causality or not. And this becomes even more problematic in smaller systems. This was done for heavy ion collisions. For more on this, so there's the QGP6 book is coming out, and you can already look at the contribution that we wrote on the small systems, and that's the reference here. I think I don't have much, or I'm already over time, I think. So I don't want to break my record from last week. I just wanted to mention that you can even look at ultraperipheral collisions. So that's been done at the LHC, where you look at collisions where the lead ions actually pass one another. So you have a photon colliding with a nucleus. So you only have the photon field of one interacting with the other nucleus. And you can measure V2 in events where you produce many particles in such a collision as well. And you see in this plot from Atlas that these solid points, the darker red and darker blue ones, are the ultraperipheral collision results. And they are, on the same order as what you find in proton-proton or proton-lead collisions, right? So there seems to be also some sort of, anisotropy in the momentum distribution in these even smaller systems, if you will. And that could be described by maybe, well, in such a collision, you have actually the photon being described by a vector meson, right? So this is a quasi-real photon, but it could still, it can fluctuate into a vector meson. And then the vector meson could collide with the nucleus. And that's a similar situation as a proton colliding with a nucleus, right? So instead of three quarks, you have two. So here I have the two quarks, and then I also have one dot for like the soft cloud that we include as well. So you have 4 and 3 hotspots in the simulation actually. I don't want to go through this, but this is just saying the energy of the photon can fluctuate, and that's important actually to describe the rapidity distribution. So here we fit everything to proton-lead. So we describe proton-lead charge particle distribution very well, and the prediction is for gamma lead is this, and that actually works out surprisingly well. Initially, we didn't include the energy fluctuations of the photon, and that wasn't so well described. But with that, you get a very good description of the data. And this is the V2 proton lead was fitted to, and then the model prediction with that constraint is here for the gamma lead. Works very well. For V3, however, it doesn't really, right? So proton lead works well, but gamma lead underestimates that data. I don't know why. Maybe the data is overestimated because of non-flow, etc., or the model is just not perfectly describing the triangularity, right? So this is really pushing it to very small systems. And there's also other predictions from just the CGC, color gas condensate, where there's no final set effects. They also can describe this data well. To distinguish these models, you could try and see what happens to Q-squared dependence at the EIC, right? So now we have basically we have real photons basically, but if we had this Q-squared handle, that should affect the effective size of your vector meson or your QQ bar dipole. And then when you change this effective size, so we call it B squared here, actually in the hydro calculations, this increases the V2, whereas in the CGC, it decreases the V2. So this would clearly distinguish these two descriptions if we can measure something like this at the EIC, for example. Okay, I'll skip this. This is more you can do with light ions and can learn about the nuclear structure. And then just two more recent things in the 3D hydro. We did a Bayesian analysis and can now extract eta over S as a function of baryon chemical potential, for example, by looking at beam energy scan data. And another thing where this baryon junction that I mentioned in the beginning enters is comparing the charge and baryon, electric charge and baryon charge stopping in isobars. And depending on whether you have baryon junctions or not, you get different results for this ratio, which I had put here, but it's disappeared. So it's a ratio between essentially electric and baryon charge stopping at mid rapidity. And if baryon charge and electric charge are stopped the same way, you get the green curve. If they're stopped differently, and you also include the neutron skin of these guys, then you get the blue curve. And if you ignore the neutron skin, you get a red curve. And the star data lies on the blue line. So it's very interesting, actually. That means you might have baryon junctions, more baryon charge stopping than electric charge stopping. And also the effect of the neutron skin is visible, because otherwise the data should lie up here. Anyway, so there's a lot going on you can do with 3+1D hydro simulations, in particular now with beam energy scan data and all the nice rig data that's still coming out. And as a summary, hydrodynamics has been very successful, obviously, in describing heavy ion and also smaller system collision data. Transport properties of nuclear matter and at high temperatures and densities have been extracted and are being extracted now with sophisticated Bayesian analysis, for example. We learn about particle stopping and particle production, and can even learn about nuclear structure properties like the neutron skin or the shapes of light ions, etc. Small system collisions features strong final state effects, it looks like. So everything we see points at that the systematics is well described by final state effects, whereas other alternatives, which I didn't go into much, but like CGC calculations often have opposing trends with multiplicity or system size than what the data shows. But the final set effects kind of describes qualitatively very well. But fluid dynamics is used at the limits of its applicability. So we see violations of causality, for example, in typical simulations, or we see a large Knudsen or inverse Reynolds numbers. And the question is, how does this quantitatively affect the result? And how can we improve on that? And yeah, but this is still ongoing. And so basically the last paper I showed you, right, that was just from a few weeks ago, where they studied these effects of causality. So this is ongoing and you know, an interesting direction of research. All right, thank you very much.
Super, Bjorn, that was great. A lot of really interesting results at the end. Questions from the audience? Oh yeah, great. Go ahead.
I had one about looking at the limits of where you can apply hydro. You're talking about where hydrodynamical modes dominate. I'm not very familiar with hydrodynamics. What actually is the description of a hydrodynamical mode, sort of outside of the fact that hydrodynamics works on it?
Yeah, I think briefly it's just the modes where omega goes to 0 as k goes to 0, right? These are the sorry, where is it? So if you do the Fourier analysis, right, of your microscopic theory, you will have different types of modes in your complex plane. Where did I say this? Here, right? And then the non-hydromodes typically decay quickly, whereas the non-hydromodes are the long-lived modes, right? And this is how you distinguish them, right? So basically in the limit of small wave number, what happens to this mode, right?
Okay, yeah.
And so these are the modes that do survive the longest, right? And then you can say, okay, after everything else is gone, then the system behaves like hydrodynamics, because only these modes are left. But what distinguishes the different theories, right, is basically just the non-hydrodynamic modes, right? So you see these differences only in the beginning, and in the end, right, at long time scales, right, this is what you expect, right, as hydrodynamics as an effective theory. It's supposed to describe the long distance and large time scales of any system, right? Given that you put the right viscosities. That's why these things are scaled with the viscosity, for example, right? So as long as you're looking at the longer time scales, right, any system should be described by hydrodynamics, as long as it's well, still interacting, right? Yeah.
Okay. Great. Cole, please go ahead.
Yeah, I had a question about the hotspots that you use inside protons. So there's, you said that there were 3, which makes me think, I mean, it's motivated by where the quarks are, I guess. How, I mean, and then you transition to thinking about it as a sort of CGC where gluons. So why do you expect that where the quarks are then motivates there should be gluons nearby, or what's the idea there?
Yeah, that's sort of the idea. I mean, this is how we started doing this, by just looking at like 3 hotspots. That was the idea. We were saying, okay, maybe if the gluons are sort of seeded by the valence quark structure, right? So the large x degrees of freedom, there should be 3 to first approximation, right? And then you can think of dipole emissions and radiation and so on, like a small x evolution, which then would develop where the gluons are. That's a kind of rough approximation, right? You could have more large x degrees of freedom, right? You could have a splitting of these guys into harder gluons, for example, or emission of harder gluons and splitting into QQ bar that are harder. So you could have 4, 5, 6 more hotspots. So we tried different things actually. For example, we did a Bayesian analysis where we had the hotspot number as a free parameter. There we find that in some cases it looks like maybe 7 or a larger number is preferred. But it's not a strong difference depending on whether you use 3, 4, 5, 6, or 7. Another thing we tried is actually not putting the gluons around these quarks, right, with a Gaussian just around the hotspot, but use some sort of stringy model where the gluons are sort of in between, right? So you have these Y-shaped, you could have like a Y-shaped or distribution.
As in baryon junctions.
Yeah, kind of like in a baryon junction, if you will, right? And so we parameterized that by the width of such a leg of this Y, right? And then we had that fluctuate. So we had the ends fluctuate, just like we have the hotspots positions fluctuate, and then also the size of that string. It didn't give us much different results. And so we stuck with what's easiest. Right? Because I mean, of course, this is all phenomenologically constructed things. So it's easier to grasp what's going on when you have like just the 3 hotspots. But it doesn't have to be 3 hotspots, right? So maybe if one revisits this, maybe one can find observables that are sensitive to whether you have 3 blobs or you have these stringy structures or so. But from what we had looked at back then, there wasn't much of a difference.
So the stuff that you talked about at the end, right? Things that would differentiate baryon stopping from charge.
Mm-hmm.
Is that a candidate? That's plausible. Could one do something as a practical?
I'm not sure, since that depends also on a bunch of other features, in particular in the longitudinal direction, right?
Yeah.
I don't know if it would constrain this. Yeah, I'm not sure. But certainly, I mean, on the level of baryon number, right? It does distinguish. At least it distinguishes whether the charge follows the electric charge follows the baryon charge or not. So that kind of distinguishes sort of the valence quarks degrees of freedom from the rest. Yeah, so I don't know. Maybe it could help. But I think you need additional observables as well.
And not that sounds simple at all. I mean,
yeah.
disentangle stuff.
Yeah.
Okay. Sort of something about follow-up question. Near the end, you were showing these virtual photon interactions and going through all the data except for the V3. Yeah, let's get to that and take a quick look to remind. Yes. So I guess 2 questions for this. One is, first, you are describing, let's see. So I remember there's an earlier plot where the proton lead was not well described. And I think you are describing the proton lead well here. And so what's the difference? And then the second thing is, I don't think you ever showed proton-proton collisions. And is there a reason why you've not in any of these calculations?
Right. So this is the 3D Glauber model, right? So this is not the IP Glasma that I showed you PLED in the very beginning, which was somewhat below the data. In addition, as I said here, we actually fit everything to PLED, ignoring everything else more or less. So I don't know actually with this setup how well LED would look. I think it would still look pretty good. But this is actually, everything is tuned to describe PLED.
I see.
So that's why this looks more or less perfect in PLED. So that was sort of our baseline to then predict the gamma LED, right? Based on that. So we said, what if we have a more or less perfect simulation or description of PLED? What would we get for gamma LED, right? So that was the idea here. That's why the PLED data looks so good. But it's also a different model than what we used in the plots I showed earlier for PLED, right? I had only shown this model here for RIC originally, right? I only showed the system scan. But actually there we also used PP. So as I said, we kind of tuned things to proton-proton. So the proton-proton multiplicity distribution here on the right, and then the rapidity distributions. We don't have proton-proton VNs at RIC. I don't know actually if there's data on that at RIC. I don't know. But we have not looked at the VNs in PP, if that's what you're referring to, with that model. Because if we looked at it here only at RIC, certainly there's LHC PP flow data, but here we focused on RIC, and then LHC we only did this used this model for the UPCs, and we haven't looked at the PP there. Yeah. Was there any PP here? No. Yeah, no. But indeed, I mean, we looked at PP for tuning the model actually, right, and getting these fluctuations.
So at what stage do you try to compare to all the world's data in, ultraperipheral plus proton-proton plus proton A plus AA?
You mean like in a global analysis kind of thing, or?
Yeah, of some level of sophistication, maybe not necessarily a full Bayesian, but you say here you at the very end you had this beautiful comparison peripheral that PLED, but what about say proton-proton and AA, even at a qualitative level within that one model?
Yeah, no, I think that you can certainly do. I think, as I said, I don't expect the LED to be far off from the data, if not even very good. But we haven't looked at with this particular tune at the LED. We will certainly try that, right? I think there are, because this model in particular has a lot of parameters. That's the downside of this 3D model, which describes all the baryon stopping and all these things, right? It's not as nicely constrained as like a more first principle calculation, like the CGC or IP Glasma would give you. So you have enough parameters, so to probably get all these systems consistent. The question is, how much do you learn from that still, right? I mean, you do learn that that there is a possibility, right, to describe everything in one, right? So that's already something interesting. Because I think in PLED, right, you will be sensitive to other things than in LED, right? You'll be more sensitive to the substructure than in LED, for example. And LED will be sensitive to something else, right? So in that sense, I don't doubt that you can do it. We haven't done it for this particular setup. Yeah. In IP Glasma, we tried to do it, right? We looked at PP to LED and also the different energies, where I showed last time that we don't describe the PP well, right? But we didn't, and then part of it may be that it's not 3D, right? As I showed you, there's a strong effect in 3D with the decorrelation and rapidity that is otherwise ignored in these 2+1D systems, which shouldn't be ignored, right? Especially in asymmetric systems and very small systems.
Very good. Yeah, thank you. I have a much clearer picture. Maybe one last question, which I've asked you before, and you sort of told me, but I'm just going to still ask it again, which is, what about the idea that perhaps the equation of state might have some system size dependence?
Oh, um, so the question is, can the equation of state have a system size dependence? Or
Yes, I mean, I definitely think it will have one, and then could that be something that you would implement, that you could implement? And then
Right.
how that could
Um,
it be?
so I think so your argument was that the equation of state has a system size dependence because you cannot in the small system resolve or fit in all the modes or the
I think so can the equation state depend on the system size? And I think the answer is yes, for reasons like you mentioned. You might expect Casimir-ish type effects, for example. And so if there is a system size dependence to the equation state, then that presumably will push through to a VN analysis, whether it becomes stiffer or softer as a result of the small size. I think the last time I nudged you on this, you felt it would be difficult to implement something like that.
Yeah, that's why what I was thinking now again, right? Yeah, because I mean it's usually you apply it locally, right? Where the equation of state is assuming you have a fully thermal system in every point, right? So you would have to know about everything. So in a hydro cell, right? You use your equation of state, irrespective of what's the neighboring cells do, right? If there's already no more energy density next to it or not, right? So you would have to somehow know about the system size in every cell, which usually you don't know, right? In the simulation. You would have to feed in information into every local cell about what the entire system looks like, right? I guess that's possible. Yeah, it should be possible, right, to kind of convey that information to the cell. Is it physical for it to not get that information? I don't know, right? I mean, potentially, yes. I mean, if you're saying it cannot, yeah. So the system size dependence to the equation of state, quite generally, is it an off equilibrium effect? It's not, right? It's still equilibrium,
Yep.
but it is, yeah, it's a constraint. Yeah, I mean, I think it's possible, but yeah, indeed it's difficult, right? Because you have to kind of determine in every step how large is the overall system, and that's anyways with the fluctuations not so easy, right? Do you do it locally, right? If you have a hotspot, or do you do it globally of the entire distribution? So what are your quantities, right? You could maybe get some average size by weighing, with energy density and looking at what's the area, right? That's above some threshold. And then that number you feed into every cell, right? Tell the cell what is it, and then modify the equation of state that you use according to that. So that might be possible, yeah.
Yeah, that sounds super interesting. Yeah, that would be really neat.
Yeah. So yeah, I think there's ways to do that. I have to understand a little bit better. I think you have a paper on this, right?
Yes, well, where we start to look at changes to pressure and energy density,
Yeah.
system size, it turned out that, and Peter Petresky helped us understand intuitively why, but without doing any quantum corrections, the system always has E is 3p for a non-interacting gas.
Mhm.
To get deviations from
Mm.
that, you need to have the anomalous scale breaking from quantum effects, at least from the analytic side.
Uh-huh.
But I feel like the lattice people, I mean, to get their equation of state, they extrapolate from small systems. So they must have small system equation of state data lying around just somewhere on their hard drives.
Mhm. Well, at least they do, yeah, do they do smaller system or just larger lattice spacings?
Oh, well, I mean, they only have a finite size lattice, right? So that is right there a finite size system.
Yeah, I don't know if they changed the lattice length, right? The infrared scale essentially, right? Or if they, keep that fixed and just change the lattice spacing when they, when they want to do their continuum extrapolation. Right? You have those two handles, and you were probably interested in the overall length of the lattice, right?
Yeah, the overall size of the system,
Yeah,
but
right.
they might have some nx, for example, number of sites, and then whatever a is, that tells you how
Yeah,
big it is.
right. Sure. It's just the question is, do they vary the n and keep a constant in some cases, right? Because then you would get the dependence on the overall size, right? If they change a and n together and keep the size fixed, then you don't learn about the size effect, right?
I think both. I think both ways would give you different information.
Yeah, sure. I mean, one is the UV and one is the IR in a sense, right? But I think if you're not varying the IR scale, so if you're not varying the overall size of the lattice, I don't know how you learn about the system size, right? If you're only changing A and N together, right, and keeping the system size fixed, I wonder how you would learn about what you want to know, right? How does it depend on the overall size? But maybe they do that. I don't know, right? I don't. But usually, I think they're changing just the A. I'm sorry. They're changing just the A scale, right?
I don't know, maybe something worth chatting with some lattice folks about if you would be interested.
Yeah, sure. I mean, it could very well be that they have looked at that as well, right? In principle, they should and learn about the dependence on the size, right, on the IR scale.
I definitely think so.
Yeah.
Actually, so Azundini, I don't know if you put your hand up more recently. I apologize if you've had your hand up for a while, but please go ahead.
Yeah, no worries. You had quite interesting discussions. I've got probably just two questions, and one is on the causality studies in the plane of the coefficients, the pre-coefficients of bulk and shear viscosity in that plot, and versus the fact that now you are able to extract eta over S in the experiments. And one wonders whether that can come and actually shift this bulk shear relaxation time plane. If you now know the coefficients themselves, whether one can come and see if this will still stand, whether the causality region will shift, because it looks like it depends on these parameters, this region.
Sorry, I didn't get what you mean in terms of how it would shift.
So this is not this is not from experiments. The constraint on this region, it's
Right.
phenomenal,
Yeah,
right?
that's not from experiment. No.
Yes. Now, experimentally, now you can extract eta over S. So I'm just wondering whether that extraction will probably come and have an impact on where the region for the causality region should lie.
Oh, I mean, I'm not sure. I mean, that's kind of what they do, right? They use experimental data to extract the eta over S, right? So this has experimental data input. And the difference between these two curves here, or these two bands, right, is whether they allow their results to also lie in the acausal region. So they get some Bayesian posterior, right? And then some of the parameters in the posterior that they sample from the posterior, right, they will lie outside this region that they determined from their conditions, right, independent of experiment. And then they get the purple band. And if they just remove those from the posterior, they get the blue band. So first of all, it's not a big effect, right, on the eta over S, for example, right, whether you enforce this or not. But what you're saying, I don't know whether it kind of you kind of saying it could like you mean it could change the gray area here? I don't think it
Yes.
would, right? Because this is purely from theory, right? And then experiment just tells you which are the preferred values, right, of these. And they either lie in that region or not. And then, yeah, what they do is then kind of just, if they're not, they either remove them or not. And that gives these two different bands. So that's just, for me, that just, I mean, this is not my work, but for me, this just means that for eta over S, it doesn't matter too much whether you allowed this to happen or not, that that you have acausal regions, right? And this is a very strict cutoff. I mean, they don't remove all the events where like one cell sometimes, is in the acausal regime, but I think the total energy in the system that's in acausal cells divided by the total energy, like everything, has to be less than 0.00001% or so. So it's a pretty strict constraint here, right?
Okay, no, thank you.
Yeah, I hope this roughly answers it. I mean, this is at least how I understand it. Yeah, I just read this week and I found it was interesting, so I thought I added it. No.
Wonderful. Okay. Anyone? Oh, yeah, cool. Yeah.
Yeah, just also maybe more generally on these Bayesian analyses and extractions. It seemed throughout the talk in a few places there were sort of modifications to the theory, so say like including the subnucleonic fluctuations, like kind of improvements, or including the nucleon-nucleon cross-section, which seemed to quite dramatically change, or at least like say in the case of the W parameters, what I'm thinking, where before the theory could kind of compensate between say the nucleon size and eta over S to get what you needed, including more constraints, sort of remove that freedom. Is there a concern that there's some other stuff, improvements to the theory or more constraints that we haven't thought of, which would then dramatically, change the interpretation of these various extractions? Like maybe you get quite a different value now that you include some other part of the theory, and then is there a way to a priori know whether, we have to worry about that or not? Like I always kind of struggle to interpret these extractions, I guess.
Yeah, I mean, generally, I would say your Bayesian analysis is only as good as the model and the information you put in, right? You're definitely constrained by the model, right? If your model doesn't have the physics, and that's important physics, whatever, you can do the best Bayesian analysis, it won't help you much, right? So yeah, there is a concern. I mean, I don't expect that, we will find something that we missed that will lead to eta over S coming out as 10 times larger than it is now, right? I don't think so. There's not going to be a great change, but in terms of, for example, details like the temperature dependence, right, or the bulk viscosity, even normalization, right? So there we don't know really within a factor of 2 or 3 how large the peak is, right? So this is the band they get, but if you change your initial state model dramatically, right, you have a much more compact system that would produce more transverse flow. You would need to compensate with a large bulk viscosity, right? Of course, they have parameters also for the initial state model. So this is all being constrained together. But if they're, missing some physics in there, right, that will lead to different energy deposition that their model doesn't cover, indeed, then there could, you could get different results. So these things are, they're useful tools, but they're of course limited by what you what you put in, right? And that's always a concern. And yeah, as you say, there were some examples where like some fundamental observable, like the nucleus cross-section, right? If you don't include it, you may get factors of 2 difference for a certain parameter, right? Yeah, that's always a concern.
Thanks, yeah. Cool. All right. Well, Bjoern, you've really given us an enormous amount of your time, and we really, really appreciate it. And I hope you don't get sick, or if you do, it's better very quickly. But yeah, thank you very much.
All right. Yeah. Thank you. And thank you for your time as well.
Oh,
And
absolutely.
the
This is
invitation.
Yeah.
Absolutely wonderful.
Yeah.
How do I stop?
And
Here.
all right, super.
Okay.
Take care,
All
Bjoern. You.
Yeah. You too.
See you next time.
All right.
Goodbye.
Bye.
Bye.